Very welcome.
Okay, thank you very much, Andre, for your nice introduction and also for your kind invitation. So today I'm going to talk about a recent joint work together with Peter Eisenbacher and Christoph Thaler, both in Bochum, on the topics about optimal variance gamma approximations on the second Wiener chaos. So here is the outline of my talk. So I started with the section 1, which is about the Nordenpeck-Katte-Malyow-Wittgenstein's method, just for those who might not be familiar with these topics, you know, if there are any, and at the same time to provide, you know, some kind of the motivation and the background of my talk. And then I moved to into the problem of the optimal approximations in this setting. Later on, in the chapter, in the section 3 and 4, I go to what our contribution is here. All right, I'm going to pretty fast on this section. So maybe a good starting point is to come up with these classical theorems from real analysis. If you have a function, it's a deterministic result, you know, is a score integrable with respect to Gaussian measure on the real line. You can nicely decompose this over the Hermite polynomial. So I see personally myself, you know, a stochastic version of that, which Wiener-Ito-Kaste decomposition, which essentially says that if you have a Brownian motion on a probability space, and if you take any score integrable random object, you know, then you can decompose this object in this format, which the expectation plus some infinite sum of the random objects is coming in the infinite sums, which I denoted this by IP of FB, which is this or the so-called multiple Wiener-Ito integral. So this is a deterministic function inside the kernel, and you take the iterated integral with respect to underlying Brownian motion. So and this kind of the object is going to be essential object, random object, which is going to consider in this talk. So as you see, when the order f is deterministic, you get the Gaussian distribution in there. But as soon as you take one iterated integral, you know, you have a lot of new distributions comes in and play role, and as the order of the iteration integral is getting higher and higher, more and more complex distributions come in. And then the notion of the Wiener-Kell of order P. So we look at this random object of that form. We take the closure with respect to L2 norm. So in other words, you know, this Wiener-Ito-Kaste decomposition essentially says that you can diagonalize the L2 space of the Gaussian underlying Gaussian functionals, you know, Brownian functionals over the Wiener chaoses. So Wiener chaos of order 0 is just a constant, which reserved for the expectations, and Wiener chaos of order 1 just the Gaussian one, and Wiener chaos of order 2 and so on is coming on. So now why I'm talking about this Wiener chaoses is because
oh, sorry.
Sorry?
No, sorry.
Sorry,
okay.
Please mute yourself, except the speaker.
All right. So now the interesting result by Nullart and Peck-Katte in 2005, they proved that if you take a sequence of the random object which come from the fixed Wiener chaos, right? Then convergence to the Gaussian distribution, in order to have a CLT for this kind of the random object, it's enough to check on essentially the convergence of the force moment to the tree, and the tree is not a magic number, it's just a force moment of the standard Gaussian, right? So this is quite surprisingly, because before the one of the classical device, we had it in the probability theory to prove CLT is the method of the moment and cumulants, which essentially one has to check convergence of all the moments of cumulants in order to prove justify the CLT. But now they prove that if your sequence comes from the fixed Wiener causes, then only force moment convergence of the force moment is enough, you know, to guarantee the validity of the CLT. And if you later after, Ivan Nordon and Giovanni Peccati observed that you can combine Einstein's method with the Maliovian calculus in order to not to provide a new type of the proof of this result, but at the same time quantify this kind of the force, this kind of the theorem. And now this domain, known as the Maliovian-Einstein's method, you know, found its name as that one. Which is essentially tells you that if you're on the Wiener space, you take a random object X, which is smooth enough in terms of the Maliovian differentiability, you assume it's centered, and you scale it to variance 1, then you can quantify in the total variation distance how far is the law of X from the Gaussian by this quantity random object in the right hand side, which I'm just telling to you what this notation is, just in case. D is the Maliovian derivatives. L inverse is the inverse of the Ornstein-Uhlenbeck operators on the Wiener space. This is true, and for any nice random object. But as soon as your random object X comes from the fixed Wiener chaos, then by this nice identity with just the definition, you can kill this L inverse by this identity, and then you end up with this variance of the norm of the Maliovian derivatives. And the question is that now the nice thing is that if you're inside the fixed Wiener chaos, then this variance of the norm of the Maliovian derivatives can be bounded from above by the force cumulants, which is just the difference between the force moment minus 3 in this case. So this is the magic inequality, somehow, let me to call it. When you are in the fixed Wiener chaoses, you have this kind of the equality, and up to now there are at least, as far as I know, 4 to 5 different proof of this inequality. This plays now this idea how to combine Einstein's method with the Maliovian calculus, you know, is amenable to many different spaces. It's just not about the Wiener space. So you can do a similar type of the analysis on different type of the spaces, like a Poisson spaces, and has a lot of applications, you know, in the stochastic geometry and mathematical statistics, as far as I know. So let me very quickly, because I'm talking in my to the one of the best school on the Einstein's method in the world, so maybe I should skip this very quickly. Just Einstein's idea, you know, in the normal approximation. This is just easy exercise of the density of the standard Gaussian distribution. So by integration by parts, and then Einstein's observed that this operator, first order linear differential operator, which is inside the expectation, also is going to fully characterize the standard Gaussian distribution in that sense, which I define it here. So if you take any other law which is going to satisfy here for a large class of the function, then the law of the X has to be close to the standard Gaussian distribution. So this, and then then you take your underlying the probability metric of your interest, which is some kind of the integral probability metric. With the integral probability metric, I mean the probability metrics you can write in this form for a nice class of the test function HKL here. For example, many of the interesting classical probability metrics can be written this way in the integral probability metrics, like variation distance or total variation distance or Kolmogorov distance. So these are pretty classical things. Let me to skip that one quickly. And then you build up the Stein's equation. And if you'll be able to solve this Stein's equation, which is the case in this case because of this nice identity here, you can solve this equation, which is known as Stein's equation. And then you wrap up everything, and you see to controlling the left-hand side, in the definition of the integral probability metric, it's enough to control the right-hand side, which now L is the Stein's operator for the Gaussian distributions. So we end up to the right-hand side. So in order to control the left-hand side, we are going to control the right-hand side, which is the case in many different setups. This is going to be much more tractable, in particular, for example, when you are on the Wiener space using the Malyovian calculus. There are many other different methods, to controlling the right-hand side, depending on the setup. And then this the Stein's method is going to be completed somehow. You have some kind of the knowledge on the solutions of the Stein's equation, which with this means that you have some sort of the universality results on the solutions of the Stein's equation, which is somehow tells you that this is going to be independent. Some kind of the properties of the solution is independent of the underlying test function you're taking from the class of the test function HKL. All right. So how this going to work in this case gives me 1 minute to how this works, to prove the force moment theorem. So I started with the elements in the fixed Wiener calculus. I know on the Wiener calculus the elements are centered, so the expectation is 0. So I just scale it the variance to 1, and there is a nice tool, the Malyovian integration by parts formula on the Wiener space, which essentially tells you that you can write the expectation of the products as the product expectation, and the price you have to pay is a term which is right here, which is this. You see the Malyovian operators raise it up here. Now I'm going to use the Stein's equations. Remember, this is my right-hand side to control it. Right, so I'm going to use the Malyovian integration by parts formula on the second term here to produce f prime and take the f prime as a factor. I end up with this quantity just for free. Now I'm using universality results of the Stein's, taking out f prime, which is independent of the test function, and then I just doing Cauchy-Schwarz inequality. Here I end up quickly with this. Just everything's come almost for free for me. Now the message is here. The law of the Gaussian is the law of the underlying the random object, which I take it from the fixed Wiener calculus, is going to be close to the centered Gaussian. As soon as the norm of the Malyovian derivatives of that element is going to be close to the P. P is the order of the Wiener calculus. So that's the message to me. So then the proof is going to how to control that from the norm of the second derivative of the Malyovian derivative. The norm of the Malyovian derivative from the P, which is the order in the L2 sense, to control with the force moment -3. There are, as I said, there are different type of the proof, but the proof they have it, in that paper is based on the product formula. They decompose both random objects on the Wiener space, on the Wiener calculus, and then they compare, the coefficient, and they figure out this is the case. So the message at the end of the day is that the law of the chaotic random object is X is going to be close to the standard Gaussian distribution as soon as the first moment, second moment is close to 1 and the fourth one close to 3, right? As you see here, there is a square root here, and this square root come from the Cauchy-Schwarz inequality. There was a study that reveals this Cauchy-Schwarz inequality makes the rate of the convergence suboptimal. And then after some years, in 2015, Nordlin and Pecati proved this theorem, which tells that in order to kill the square root, then the third cumulant is also coming to play a role. So you see, this is going to be an optimal rate of the convergence in the quantity force moment theorem. And you see the absence of the square root here, and the surprise is that the fight between the third cumulant and the fourth cumulant here, and many occasions, and you see this is going to be a better rate, because one occasion is that if your sequence which come from the fixed Wiener chaos is going to, the order of the Wiener chaos is going to be odd, then there is a result that tells you that the third cumulant of the odd Wiener chaoses is going to be 0. So this term is going to be 0. So they could improve the rate by half. The idea of the proof here, which I'm going to use later on in my talk, is that I need to introduce new notions of the iterated gamma operators on the Wiener space. So which are defined throughout this here iteratively. I take a nice object on the Wiener space and I define these iterated gamma operators recursively. The gamma 0 is the gamma, and defined it as the gamma I plus 1. I'm just taking this as a definition. As the motivation is that when I'm doing Malyovi integration by parse formula on the gamma I, this is the compensation term which is coming here, as you see. And when for example, the gamma 1, if you're recalling the gamma 1 is the quantity that played major role in the CLT on the Wiener counts. And there is, apart from that, there is a nice relation between these gamma operators and the cumulants and the moment of the underlying objects is that the expectation of these gamma operators is going to be related with the cumulants of the random object throughout this formula. And there is another nice observation is that this, as soon as the order of this gamma operator increases, as of course the complexity of the random objects is getting also higher and higher. But the good message here, they observe that this gamma operator, when you are iterated, this quantity are going to be smaller and smaller. And this is one crucial observation they made it to prove this optimal force moment theorem. Let me to explain very shortly how this is working. Which I'm going to use this idea later on. If you remember, to prove it, the quantity force moment theorem using the Einstein's idea. So we just understanding to here, and then using the Malyovi integration by parse formula here, we produce this f prime, and then the gamma 1 minus 1, right? Now 1 is the mean of the gamma 1. Now, in order to use the Einstein universality lemma to kill f prime, take it out of the expectation, we don't do that now. Now we take the advantage of the f prime as a new test function. We look at the solution f prime consider f prime as a new test function, and then we repeat the Einstein's method once again here. Doing that, which I'm going to say these repetitions of the Einstein's method. So, we are not going to do the Cauchy-Schwarz and the Einstein universal lemma, and instead look at the f prime as the new test function. So they just write it this again, look at this, you can subtract this minus expectation for free because this guy has expectation 0. And then again, you repeat Einstein's equations, Einstein's idea, Einstein's method on this term now. So doing that one, you produce it, you know, the right quantity you're interested in. Now, if you're producing this and then the higher gamma operators comes. Now, if you do Einstein's Cauchy-Schwarz here, because of the power 2, you end up with the right quantity of your interest. And then next to it, you produce the gamma operator, higher gamma operator, which are essentially a smaller quantity, which you can control it with the right rates we are interested in, the maximum of the force and the third cumulant. So the whole message was here, not doing Cauchy-Schwarz, but instead repeating the Einstein's equations once more, and you can keep going to that one to produce the right quantity of your interest. All right. So now I think I'm ready to move to the rest of the talk, to my my topic. So today I'm going to look at the variance gamma distribution. So this is not the original definition of the variance gamma distribution. I'm just taking this as an advantage because this is quite simple for me to understand this class of the probability distribution rather than the given the density function, which is quite complex function. So the variance gamma distributions up to a random scaling, random shifting. So it just you randomize the variance of the Gaussian distribution with the gamma distribution V here, right? So this is the class of the probability distribution I'm going to consider. As far as we could track in the literature, you know, this type of the distributions appears in the financial type of the papers, goes back to 90. We could find the paper by Madan and Seneta, and also Madan and Carr and Chong. So they are using this kind of the distributions in the financial context. And also I have to introduce a centered versions of the variance gamma distribution. Variance gamma distribution doesn't have a mean 0. And I'm interested in the converging to variance gamma from the fixed Wiener chaos. So because the fixed Wiener elements in the Wiener chaos are centered, so I am going to center my target distributions, which are the variance gamma, and call it those centered variance gamma distribution with the subindex C here, which means that I make it by shifting the mean equal to 0. And now the question comes, you know, natural question, why I'm interested in this kind of the target distributions. And there is a nice result by Ivan Nordan and Guillaume Pauly, which is some kind of the stability result, which tells us that if you have a sequence in the second Wiener chaos, which you know is going convergent distribution to some target distribution, which are denoted by X infinity, then the X infinity is in the law has to be an element which is going to be decomposed only on the first 2 Wiener chaoses, right? So in other words, you know, there are not other contributions of the higher Wiener chaoses. And this result is only true for the second Wiener chaos. And this is a big conjecture. People believe this is the case for the higher Wiener chaoses, but that's open still. So now if I wanted to converge from the second Wiener chaos to the variance target, variance gamma distribution. So because of this stability results, I have to prove that I have nice intersection with this class of the variance gamma and the second Wiener chaos. And this is the case. Essentially tells this proposition here, tells us that we have quite large intersection between the class of the variance gamma distributions and the element and target distribution in the second Wiener chaos. And the intersection, we have an explicit form of that form. All the elements of that form is going to be in the intersection. And that's enough for our purposes, because many of the target distributions which we are going to observe, you know, in the limit, it takes this kind of the form in the limit. So this proposition, together with the stability result of the Nordau and Polis, tells me that so what we are going to prove later on for the target variance gamma approximation, so it's not empty result. So the other ingredients is that which, as you may expect, is the Stein's method. Now we need the Stein's method for the variance gamma distribution, and thanks to Robert Gaunt, who studied this problem starting with his PhD, and he produced an interesting result in this direction. So I'm just collecting the one which I need here. The Stein's operator for the variance, center variance gamma distribution is given by this second order ODE here with the polynomial coefficients. This is one result he proved. And also he proved nice estimates for the solutions of the associated Stein's equation. The associated Stein's equation for this Stein's operator satisfy in this following nice result. These are the counterpart of the Stein universality lemma in these settings of the variance gamma. You have a controls on the supremum norm of the f prime and f prime prime throughout the test function itself and its derivatives. And also he managed to prove the second part recently, if I'm not mistaken, last year. He also managed to prove the third derivative of the solutions of the Stein's equations can be bounded by this the first and the second derivatives of the test function. So which we are going to use this in later on a lot. So these are the result from the Stein's equations, Stein's method for the variance gamma. Later on, also a result by Peter Eisenbacher and Christoph Teller in 2015, they also combined this idea of the Malyovin method, Malyovin calculus, the Stein's method in the variance gamma approximations, and they proved this kind of the quantitative limit theorem for the variance gamma approximations. So you see, because the order of the Stein's method, Stein's equation for the variance gamma is a second order ODE, so this naturally produce higher gamma operators in the quantity in the right hand side. Remember, for the normal approximations, the gamma 1 only appears in the right hand side. Now we have also contribution of the gamma 2 operator, which is much more complex random object compared to the gamma 1. And again, you see, this is the square root of the square roots naturally come from the Cauchy-Schwarz inequality. And now the question is that, okay, we combine this Malyovin calculus with Stein's method for the variance gamma, we end up with this nice quantity in the right hand side. Okay, the natural question that comes, whether I'm able to control this quantity here by terms of the finitely many moments or cumulants, right? Like the Gaussian approximations on the Wiener calculus. So this is what I just tried to say. So whether this is possible, and this is surprisingly an open problem in the field, as soon as we move to higher gamma operators an element in the fixed Wiener chaos. So these are going quite complex random objects. We don't know how, when you decompose it on the Wiener chaoses, we don't know how to encode, you know, the coefficients and compare with the coefficient of the corresponding cumulants, which we are interested in. The only partial answer is that when the elements come from the second Wiener chaos, then there are a lot of rooms to play, and there is a partial, and the result is, the answer is yes, because, and the reason is that when your random object f comes from the second Wiener chaos, when you apply these gamma operators, they are going to be stable in the sense that this gamma operator is going to stay in the second Wiener chaos all the time. And this is not the case for the higher Wiener chaos elements, you know. So as soon as f is the second Wiener chaos, then one can write this variance of the gamma operators quantity in terms of the cumulant which we are interested in. You know, you see, it's up to 6 cumulants are coming, and this is exactly the goal of the Malyow-Einstein's method somehow, to me, that to find statements of the convergence of the distribution to given target distribution of your interest in terms of the convergence of finitely many moments and cumulants. And this is the case here. If your sequence comes from the second Wiener chaos, and then convergence to the variance gamma distributions on the second Wiener chaos of your sequence, then this is enough for the convergence to variance gamma is enough to check the convergence of only the first 6 cumulants, right? Again, as you see, there is an appearance of the square root here because of the Cauchy-Schwarz inequality. So in the last 10 or 15 minutes, my job is going to explain you how one can remove this square root from here in this setting, and then at the end of the day to provide one example, you know. So now we are going to mimic the same idea of Nordal and Peccat in the optimal normal approximation. So if we do apply the Einstein's method for the variance gamma approximation, we end up to this quantity here, right? And then we are not going to apply the Einstein universal to the Cauchy-Schwarz inequality here. We are going to repeat again Einstein's method and take the f prime of h as a new test function. So if you do so, you end up with this quantity here. As you see, the order of the gamma operator is going to increase by 1. When you do 1 times iterations, 1 times Malyow integration by parts, you end up with the higher gamma operators, right? You can do this as much as you like, depending on how smooth you are taking the original test function h, right? But the point is that you end up all the time with this kind of the gamma operators, right? So now I'm going to give you one negative result, which tells you that this is very simple example in the second Wiener chaos. You look at this kind of the sequences, and all the coefficients is going to converge to 1, right? And this is very natural or artificial sequence of the elements in the second Wiener chaos, which is going to converge to variance gamma distribution, center variance gamma distribution with this parameter here given. But the negative result is that no matter how you iterate this procedure, which I explained in a few minutes ago, resulting the higher gamma operator doesn't change the order of the convergence, right? So this is not the case in the normal approximation. This happened for this target distribution we've selected. So then if we do the repetitions of the Einstein's method, no matter how we repeat this procedure, we always end up, at least there is one quantity which the order of convergence doesn't get the right order which we are expecting to kill the square root. So then the message is that so we have to do something different with this class of the target distributions. And then this takes a while for us to understand what the different things we have to do. And doing the different things is encoded inside these propositions. Is quite involved, but I'm trying to say what is the message of these propositions is tells us that if you take element in the second Wiener chaos, in order to get the right quantity of the right order, which is here, this is the right quantity I can control with the finitely many cumulants up to 6. And now there is the nice power to 2. In order to have this, I have to take a specific linear combinations of my gamma operators to get this right order of the quantity, which is 2 here, right? That was the whole things which takes the time to observe for us. Then there are nice explanation for this kind of the inequality. At least when you are in the second Wiener chaos, we can explain this kind of why we have these variance inequalities for the gamma operators. Because of these two things, one can explain this variance inequality based on these two informations. Now we are going to use that one, this inequality here. So in order to do that, I need a linear tree copy of my suitable linear combinations of the gamma operator. So as you see here again, I'm going to take a starting point is applying the Stein's method for the variance gamma approximations. This is the Gaunt-Stein's operator L here in this setting. So I'm doing a Stein's method and the Malevich integration by parts. I end up with this. This is just the quantity which Eisenbach and Telle got it in their paper. Now I'm looking again to that guy here as a new test function. Now this is my new test function, the second derivative of the solution of the Stein's equation. Now, in order to have this nice tree copy of the different linear combinations of the Stein's operator, gamma operators, I need to somehow split this test function here in a specific manner that when I do Malevich integration by parts on that corresponding term, I can produce a common factor, which then I can use Stein universality lemma and take it out. And then I end up with the quantity which is of my interest, which is this complicated quantity inside the variance. And then when I do the Cauchy-Schwarz inequality, this is going to be square root going to be compensated with the power 2 here. To do this splitting splitting, I'm going to use a language of the operator theory. So we are going to a little bit get understanding of the Stein's operators for the variance gamma approximations. So as I said, in order to have this right quantity appears in my right-hand side inequalities, this is the case as soon as I can be able to split my given test function h in this specific form, and S is the solutions of the Stein's equation corresponding to the test function g, for example here. And the power of the S, it means the compositions of the Stein's operator. So to be able to do this splitting techniques of the test function on some kind of the space, which now here is infinite dimensional Banach spaces here, which is the space of the Lipschitz functions, right? I'm going to be able to do this one, we are going to take the use a result from the operator theory. So we look at now Stein's operator as S now Stein's operator, which means that I take H test function to SH, which means that this SH is the solutions of the Stein's equations corresponding to given test function H, right? Before I was denoting this by F of H. Now I denoted this by S of H because I wanted to take the language of the operator theory. In order to have this one, there is a nice result in the functional analysis that tells, which is about the Fredholm alternative theorem. So if I know that my Stein's operator here, which I define it like that, is going to be a compact operator. So this something requires some kind of the work to prove this operator, Stein's operator here under this Banach space of the Lipschitz functions is going to be compact operator, and also is not going to have any eigenvalues, right? Apart from 0, this doesn't have an eigenvalue. Then it means that my operator identity plus S is going to be Fredholm operator. So, and now I have a Fredholm alternative theorem, which tells me that this my equation is going to have a solutions. And of course, I'm skipping a lot of details here. One of this is that, you know, the class of the Stein compact operators is a two-sided ideals in the rings of the operators. So this is powers of the S is compact, power of S is going to be compact, the summation is going to be compact. So identity plus this compact operator is going to be Fredholm operators. And then we are using the Fredholm alternative theorem to conclude finally that this operator is going to be onto operator, which is exactly what we are looking for here, to these splitting techniques here for the test functions. So this is the novel ingredient which we bring it here in order to study this problem, to complete the problem. Now we have almost all the material ready. Now, because of these splitting techniques of the test function from this space of the Lipschitz function, we have the right quantities. You know, when we do Malyoff integration by parts formula, we produce a common factor, which is the third power of the Stein's operator act on the given test function H, and then we wrap up this operator all together. And this is exactly what we were looking for, you know, to obtain it. And thanks to Robert Gaunt's result, the third derivatives of the solutions of the Stein's operator still enjoy this universality, Stein universality lemma. Now we can take it out and use Cauchy-Schwarz inequality, but thanks this time we have power 2 in the upper bound, which is going to compensate the second power, the square root, which is coming from the Cauchy-Schwarz inequality. That's what I was trying to say, you know. Now, thanks to this power 2, the square root come from the Cauchy-Schwarz is going to be compensated with that one. And there are a lot of other terms in the upper bound, which one can tackle them to show this or the smaller than the right order we are looking for. And finally, we end up with this theorem. So we have to go a little bit weaker distance, 2 Wassersteins distance. Not exactly 2 Wassersteins distance. It's the Wasserstein distance. We have also the contour on the second norm of the test function, and this is be bounded by the first fixed 6 complement. For the lower bound, because we are in the second Wiener chaos, we have a tools, we have a we have a complete understanding of the characteristic functions of the element in the second Wiener chaos. And then the whole message is that to use this, the logarithm of the characteristic function expanded with the coefficient of expansion is the cumulants, and then to find the right domains and use the Cauchy estimates for the coefficients of the analytic functions. This is pretty classical, and this is something one can only do on the second Wiener chaos, and to get the lower bound for the optimal approximations. So this is the whole things is that okay, in our setting we could provide the optimal rate of the convergence for the variance gamma approximation based on the maximum of the first 6 cumulants, which is somehow can be seen as extensions of the optimal force moment, which is the maximum of the second, third, and the fourth cumulant for the normal approximation. Let me, in the last minute, I take very quick last minute how this can be applied, this result, in one, thanks to a paper by Bai and Toku in Annals of Probability, if I'm not mistaken, 2017. So they take this kind of the elements in the second Wiener chaos, they call it generalized, I forgot, generalized Hermite processes, if I'm not mistaken. And then in order to define this random object to be defined, this kernel must be in L2. This brings some kind of the limitations on the gamma 1 and the gamma 2. The gamma 1 and gamma 2 has to live in this square. And then what they studied, they studied a nice problem and beautiful result. They studied what happened in the convergence in the law as the parameter gamma 1 and gamma 2 is approaching the boundary of these triangles. And they obtained nice limit theorems. One of these nice limit theorem, which is interesting to us here, is that approaching this corner 1/2 minus 1/2, this corner here, which they prove that this sequence of the random objects in the second Wiener chaos converge to a target distribution, which is indeed in the second Wiener chaos, and at the same time is the variance gamma, these center variance gamma distributions. So is the chi-square distributions, each one of degree 1, 2 independent. So they prove it. Then this is exactly a limit theorem which fits in our setting. So now applying our result to this limit theorem, before there was a result, tells that, okay, this is the result comes directly because of the Eisenbach and Telle paper. And you see the square root of the here because of the Cauchy-Schwarz. And now our result tells us that one not only can kill this square root here, but at the same time, you can provide the lower bound at the same order. So we can improve this rate of convergence by 2 here. All right, thank you very much. I think it's a good time for me to stop it here. And here is a few of the papers. So the new results is based on these papers, which is in our archive now. And these are the other results which I was using during my talk here. Anyway, thank you very much.
Well, thank you, Ahsan. Very nice talk and a lot of details. Okay, just please ask your questions. Just feel free to unmute yourself and ask your questions.
I have a question. If you don't have a random variable to approximate that's in I2, can you still use these techniques to get better bounds, or does it just collapse completely?
Yeah, that's, as soon as it's not in I2, then it's going to collapse.
Yeah.
Yes, unfortunately, yes.
So even if it's nearly in I2 in some sense, maybe got a little bit of I3 in it. Or...
Yes, by the techniques available at the moment, so these are going to collapse, unfortunately, as far as my knowledge says.
Yeah, it's a pity, isn't it? It's very pretty stuff.
Yes, yeah.
Okay, for the slide 51. Yeah. So you have a very nice result there. Yeah, okay, this one here, yeah, 51. Slide 51, yeah. Okay, at the bottom, you highlight it. So if you apply this theorem to the example of independent normal random variables you presented above, how will the bound look like? Or did I ask a stupid question, too stupid to answer? Yeah.
No, at all. I'm trying to understand.
How does this look like? Because I try to digest your upper bound here, DH2. Looks like, many times in here, I don't quite digest well. So just in that example, how would that look like? Using the CIs you had above.
So you mean we're talking about this inequality here?
Correct, yes.
And now you are interested in the case F is IID?
Yeah. The example you just explained a few slides before, that you have this of this NI squared, something CI NI squared minus something.
Yes, I know. Yes, you can do some kind of the computation in there because as we said, as soon as you're in the second Wiener chaos.
Yeah. How will this look like in here? That example. Yeah.
The right-hand side, you mean? Or
yeah, correct. Right-hand side.
Right-hand side is this M of F is the maximum of the first difference of the first 6 cumulantes from the elements you selected from the target distributions. So in that example, M of F is the CII minus 1 to over 2. If I'm not mistaken, let me bring it. I try it's here. Was it here? No. It's have to. Maybe it's here. Maybe I should do like that. This is
something around here. Yeah, something around here. Correct. Yes.
You get this one, and because of there is a square root in there, the square root is kills. It makes suboptimal. And our goal was that, to somehow kill this Cauchy-Schwarz inequality rod here, which makes the rate of convergence suboptimal. So, for example, in that setting of the limit theorem by Bai and Taku, the order of convergence is 1 over n, square root of n. So, because of the Cauchy-Schwarz, now with our result, we can manage to prove it. The rate of the convergence is 1 over n, and now at the same time the lower bound. So,
thank you.
Any other questions? Any other questions or comments? Son, I have maybe a very distant question. So you did this for random variables, but if you consider the corresponding case of processes, say Rosenblatt process or similar, can it be somehow useful for processes as well? Because the Rosenblatt process, it's like some analogous of the second Wiener chaos. Yeah.
Yes. Then you're expecting to have a result for the finite dimensional distributions or the whole as a whole process?
In any matrix or whatever.
Oh, I mean, I don't, at least I don't know how to do it for even this. No, this, I don't know how you can make it. These techniques works for any marginal distributions. If you look at the as a stochastic process, because then you need multi-dimensional versions of the Stein's method for this setting. So the setup is changing somehow in my view. It's not the problem. It's not any more one-dimensional things. So, and if you go as a look at the whole process to try to quantify, then this much more. I think one needs this kind of the Barbour PTRF papers in 19th type of the result in this setting, which is not available.
Mm-hmm.
As far as we know, for the various common distributions.
Okay, thank you.
Yeah, thank you.
Any other questions or comments? Okay, so if not, let us thank our speaker again. A very nice talk. And Kostya on some stage will inform us about the next seminar. Yeah.
Yeah, it's on the web in 2 weeks' time.
Yeah. Okay, 2 weeks. Okay, I didn't check. Okay.
Thank you.
Okay, thank you.
Thank you.
To Australia,
Thank you.
at least
Okay.
remotely.